Hello, everyone, and welcome to another episode of the Data Science Decoded podcast. It's number 23 and counting. So I hope everyone are well. I'm here with Mike and Neil. How are you guys?
Doing great. I'm doing great.
Not bad, not bad. I'd like to emphasize that this episode is the third episode of the second season. Okay, because we did the 20 episode in the first season, and this one is the third episode of the second season.
And in the second season, hopefully we'll get to the 70s.
Yes.
So stay tuned. And to our listeners, you're probably missing this, but we are all wearing hats. No good reason, just because we love Nir and he had a hat, or often he has a hat, so we said we're going to join in. And
Thank you,
funny
guys.
fact, the office we're staying in with my company, they've celebrated Pi Day on the 8th of January. And I'm like, what's going on? It's not Pi Day. And they told me, no, this is the real pie, like crack pie and stuff like that. I'm like, okay.
I see.
That's cultural appropriation. Until we, the geeks, we have one day, Pi Day, and now you steal it from us. Come on. Okay, so let's go back on track. Today we have a really cool paper, which titled Equation of the State Calculation by Fast Computing Machines. And to our listeners, if you're familiar with MCMC, which stands for Markov Chain Monte Carlo methods, many people say this is the first paper that introduced it. It's from 1953, and it's by Nicholas Metropolis, Ariana Rosenbluth, Marshall Rosenbluth, Augusta Teller, and Edward Teller. So we have some kind of family stuff going on here.
Yeah.
I guess they're related.
One
Rosenbluth,
Metropolis, two Rosenbluth, and two Tellers.
Yeah, two Tellers. Yeah, that's true. They all worked back. I think they developed it in the 40s. We talked about the previous Monte Carlo paper, who was by Ulm and also Metropolis.
Mm-hmm.
And now others joined him and, let's say, improved it a little bit. And also during their time at Los Alamos, it was during the World War II. And I'll read the abstract. A general method suitable for fast computing machines for investigating such properties as equations of state for substances consisting of interacting individual molecules is described. The method consists of a modified Monte Carlo integration over configuration space. And they say results for the two-dimensional rigid sphere system have been obtained on the Los Alamos Maniac and are presented here.
This is very cool abbreviation, by the way. I love
it.
Yeah.
Los Alamos Maniac.
Yeah. That's their computer, and they had like number 1, 2, and 3. And I read on Wikipedia, Dan von Neumann didn't like the name Maniac, that Metropolis.
I'm not surprised,
Yeah, came with it. So we love Metropolis.
Yeah.
And that's why we continue covering his papers.
And we love the Maniac.
Yeah. Yes. So to our listeners, it's like around 6-7 pages paper, not long, but the gist is like around the 2 first pages. We'll try to go over them in depth, and we believe this is the important parts are there. So I'll start with the introduction. They say the purpose of this paper is to describe a general method suitable for fast electronic computing machines, today we call it a computer, of calculating the properties of any substance which may be considered as composed of interacting individual molecules. Okay, so there's a lot of molecules, they're trying to calculate various properties. And again, Second World War II, you can think why it was relevant. And
By the
they
way,
say classic.
guys,
Yeah.
I have a very, very small and related observation. We are reading a lot of papers from 50s, 60s, and they don't use the word compute. They use word calculate. Okay, and it is very interesting. Then this trend has been changed. Then calculate was replaced, or maybe sometimes used instead of it computed. So, but here in these papers, we don't see any use of the word compute.
Except computing machines, which is the
Computing machines, but
title
not to
of
compute
the paper.
something.
Yeah, that's true.
Yeah, the
So they
nomenclature
say
changes, yeah.
they say classical statistics is assumed, so no quantum stuff. Only two body forces are considered, and the potential field of a molecule is assumed spherically symmetric. So again, they're physicists, so they're trying to make things more, let's call it, easy to solve, right? And try to use rigorous math to solve. And they
By
say
the way,
these are the usual assumptions made in theories of liquids. Yeah, sorry.
question: why do you say no quantum? It says classical statistics, not classical mechanics.
That's true. Good point. Yeah. So what? So you're totally right. Doesn't
No
say
quantum
mechanics.
statistics in this paper.
No, in this paper,
Although
no. But classical statistics is not opposing to the quantum, I think.
that's true. It does not oppose. So when they say classical statistics, what do they mean by that? Like, what's not classical statistics? Like,
I don't know. I didn't understand that.
yeah, okay. That's maybe they meant that. Maybe they meant like that there's
Classical
no
mechanics.
quantum stuff, because this is what I thought straight away.
Yeah.
But you're right with your
By
point.
the way, maybe they meant that they are relying on non-fragmented statistics, and they call it classical statistics and Bayesian statistics, not classical. I'm not sure. I have no idea. I admit.
Yeah, that's a great question.
Okay.
No idea. Okay, and then let's continue. Chapter 2, the general method for an arbitrary potential between the particles. Okay, so they say, in order to reduce the problem to a feasible size for numerical work, we can, of course, consider only a finite number of particles. This number is capital N, maybe as high as several hundred. Our system consists of a square containing n particles. In order to minimize the surface effects, we assume the complete substance to be periodic, consisted of many such squares. Each square containing the n particles in the same configuration. Right? So again, just to not be dealing with boundary effects, this square is replicated. It's like a lattice. There's a lot of infinite amount of squares, just so it'd be easier to compute or calculate.
It's like, Daniel, it's like when a particle is going through to the right, it appears on the left, right?
Correct. Yeah,
Okay.
it's the same because of symmetry.
Yeah, okay.
So they say, thus we define DAB, so the distance between AB, as the minimum distance between particles A and B, as the shortest distance between A and any of the particles B, of which there is one in each of the squares which comprise the complete substance. Okay, so what they mean here, so if I take a particle A and another particle B, so in some cases, the B in the other lattice, or sorry, the other cube that is adjacent, maybe even closer to A. So then they're gonna calculate this distance, right? Because again, everything is symmetric, just for listeners. And they say, if we have a potential which falls off rapidly with distance, there will be at least one of the distances AB which can make a substantial contribution. Hence, we need to consider only the minimum distance DAB. Again, what they say here, if B, again, there's other adjacent cubes, so there's B there as well. So between A and B, there's a few distances. And then they say, because it falls as exponential, we only use one of them because the other distances is
negligible.
Yeah,
So
negligible, exactly.
yes, they assume that there is no case that these distances, these two distances to 2 points B are equal. The probability
Yeah,
of the case is zero or
Zero.
very close.
exactly. Exactly. Now they continue. Our method is in this respect is similar to the cell method, except that our cells contain several hundred particles instead of one. One can think that such a sample would be quite adequate for describing any one-phase system. We do find, however, that in two-phase systems, the surface between the phases makes quite a perturbation. Also, statistical fluctuation may be sizable. Again, not sure what they're talking about. I'm not. I studied physics, but it was long ago, and they have some kind of other systems they reference in here without the actual reference. Okay,
Next
but
time
now
we
we
invite
come to the
some.
gist.
Next time we invite some physicists on this physics-related papers, because there are a lot of stuff, not non-mathematical stuff, which at least me I couldn't understand. But,
Okay, so this is now we get into the important part. So
Yeah.
we'll try to understand that, and hopefully we'll be able to convey it. So they say, if we know the position of the n particles in the square, we can easily calculate, for example, the potential energy of the system,
Mhm.
which is summing over I and j. So there are two sums of a function called v of dij, which is this distance. So v is the potential between molecules dij, where dij is the distance. So again, the problem they're trying to solve in this paper is how to compute the summation in a way that is probably computable in finite time with the resources they have or they had back in the day. And I would like to say maybe motivation on why it's important to this potential energy, E. Okay, so as far as I remember from physics, you can derive, assuming you have E of some system of particles, you can derive other properties. Okay, and the next equation, F, they're describing also depends on this E.
Mhm.
So in a sense, once you have the E, the energy of the system, you can do some derivatives of it, etc., and maybe get velocities or get temperature or get other properties that might be interesting, like forces as well.
Daniel,
Yeah.
I actually understood it differently than you.
Okay.
So,
Please tell.
so I understood that the paper is trying to calculate easily equation number 2 based on how easy it is to calculate equation number 1 when we know the position of the n particles. So we calculate this E and we plug it in number 2. Now number 2 is an integral that is over 2n dimensions, right?
Oh, okay.
Which is very hard to solve, and that's why they introduced this MCMC method, or the special sampling method. For that's how I understand it, at least.
Okay, I think you might be right. Now that I read it, so perfect. That's why each one reads it independently. So they say here, in order to calculate, so assuming there's E, in order to calculate the properties of our system, we use the canonical ensemble. That's from statistical mechanics. So to calculate the equilibrium value of any quantity of interest F, there is, again, to our listeners, two integrals in 4 n dimensional phase space. They also say it.
Yeah.
Maybe, and then that's the more difficult part. I'm
That's
trying
what?
to think. So you say that's the difficult part to calculate.
Yeah, the difficult part. Let's read the integral. So the first integral, which is the numerator, is f times exponential of minus e over kt, and the differentials are 2n dimensionals in one dimension and 2n dimensional in the second dimension.
Yeah.
Okay, so it's 4n variable integral. Okay, over this f, and
Yeah.
and this is like the mean f times the distribution. This is called in physics the Boltzmann-Gibbs distribution, right? Or the Gibbs-Boltzmann
Yeah.
distribution. And when you calculate the mean, you basically calculate the equilibrium, but this does not sum to 1. So they have to divide by the normalizing factor, which we have in the denominator. At least that's how I understood it.
It makes sense, though I admit that I have no idea about it.
And I have a book recommendation. Maybe that's the proper. I also read it here in the book.
Okay.
And this is
okay, gotta go.
And this book is called Statistical Physics for Electrical Engineering by Professor Neri Merchav from the Technion.
Yeah, I took a course with him.
You took?
He did. Yeah, he got annoyed at me. I was talking during the class. True story. True story.
Yeah, he's a very good friend of mine.
Okay.
Yeah. Yeah. But yeah, I know what you mean. He can get annoyed.
Yeah, so I was a student. I was like a undergrad student, so that's what happens.
Yeah.
It's natural.
Yeah, it's natural. Yeah.
Perfect. So thank you for this, Neil. You see, without you, would be confused. And they even say it. It's evidently impractical to carry out a several hundred-dimensional integral by the usual numerical methods. So we resort to the Monte Carlo method. The Monte Carlo method for many-dimensional integrals consists simply of integrating over a random sampling of points instead of over a regular array of points. Okay, so this is the previous paper we reviewed,
right?
That introduced the idea,
right?
And now they are going to take Monte Carlo and improved it a little bit.
Yes.
And this is what they say here. Thus, the most naive method of carrying out the integration would be to put each of the n particles at a random position in the square, and give this configuration a weight, which is the exponent in the integral. This method, however, is not practical for close-packed configurations, since with high probability we choose a configuration where the Boltzmann exponent, which is e to the power of exponent to the power of minus e, we discussed, divided by kt, is very small. Hence a configuration of very low weight. So they're saying if you just sample randomly, those random configuration will be of low probability.
By the way, this is a Gaussian. Just to make things clear, this is a Gaussian.
What is
I thought it's exponential. You sure it's a Gaussian?
I mean, with respect to the energy, it's exponential. With respect to the, let's say, voltage, it's Gaussian. Because the energy is the voltage squared, right? And
yeah.
KT,
wow, you are smart. I love you.
The Boltzmann, thank you. The Boltzmann coefficient there in KT, the temperature is just like, think about it like sigma squared, like the variance. Okay, it's normalizing it.
Guys, do you know what this stuff which you read right now in this paragraph reminded me? Do you remember what is Langevin dynamics?
We talked about it a few sentences.
Yeah, you talked about it, Mike.
Yeah, you talked about it.
I think I talked about it. Langevin dynamics is also a method of sampling from a very complicated distribution that we can't sample in a natural way. They're given in an implicit form, and the problem with the purest form of the Langevin dynamics, if you don't add noise, that you sample mostly in the places in which the probability of being for this probability function they are sampling from is very close to zero. So they add noise. They start from some very noisy implicit distribution, plus some noise. Then they sample from it, and then they gradually reduce the amount of noise, and only then they reach the target implicit and the complicated distribution. By the way, this idea was used in the diffusion models, and diffusion models the generalization which is called score denoising score matching, which was developed by very powerful, very very talented Korean mathematician Song, maybe Yang or Song. He wrote a lot of papers, but still this problem of sampling in very low regions is a very common problem in the sampling world.
Yeah, I think what you're saying is totally makes sense because of many ideas stem from like statistical mechanics originally.
Yeah.
So for sure that makes sense, and also variational autoencoders, right? They have similar ideas.
Yes.
Yes.
Like all the concept again of energy based models, also related, which we'll cover in the future. At least I remember in around 10 years ago, even more, there was the RBMs. Remember, restricted Boltzmann machine, something.
Yes.
So also there's energy based. So we'll get to that.
Yeah, we'll get to that because I want to learn it. I don't know it now. I want to learn it, and we'll definitely discuss.
Perfect. So I'll continue. So they say because just doing random sampling will sample states with low probability, they employ a modified Monte Carlo schema, where instead of choosing configuration randomly, they say we weighting them with the exponent, and we choose configuration with a probability of this exponent and weight them evenly. So they say this we do as follows, and now the algorithm. We place the n particles in any configuration, so just like a random starting point. Let's say in a regular lattice. Then we move each of the particle in succession according to the following prescription. So x moves to x plus alpha phi 1 or whatever.
Psi, I don't know.
Psi, maybe psi 1.
Yeah, some weird Greek letter.
Yeah, and y is similar. It's moved. They take this y coordinate and they move it to y plus alpha psi 2. And they say alpha is the maximum allowed displacement, which they take arbitrarily. So again, this is some kind of a constant, but psi 1 and 2 are random numbers between -1 and +1. Right, so eventually you move randomly this coordinate xy of each particle in a random distribution
inside a 2x2 square
by alpha square, right?
Yeah, no,
the size of the square is
alpha is a random. Alpha. No, psi is a random. Sorry. Yeah, you're right. Alpha by alpha square. 2 alpha by 2 alpha.
Yeah, exactly. Exactly.
Yeah, you're right.
Guys, note that this transformation is symmetric. The probability of x getting x1 is the same probability to get x1 from x. It is exactly the same, and it will be important in what follows.
Yes.
And they say then after we move the particle, it is equally likely to be anywhere within a square of a side to alpha centered about its original position. So that's what they said. And then they continue. We then calculate the change in energy due to this movement of the system, and they call it delta capital E, which is caused by the move. If this change in energy is negative, so it means they bring the system to a state of low energy, we allow the move and put the particle in the new position. If the change is positive, we allow it with probability of this Boltzmann exponent. It's like they penalize it because it's like getting positive energy. It's a low probability event.
Yes.
Right? That's how I get it.
Yeah, guys, what is it? What do we see here? I see important sampling. We talked about that, right?
This is important.
Yeah. So
No, important sampling. No, rejection sampling.
Rejection sampling
Rejection sampling, not important. Important
is a
sampling.
subset of important sampling. Mike.
Yes.
Yeah.
Perfect. So we'll continue. Then whether the move has been allowed or not, whether we are in a different configuration or in the original configuration, we consider that we are in a new configuration for the purpose of taking our averages. So they calculate this average of F.
And that is the sample mean. That's the sample mean of Fj, right? And this is an approximation to the integral that they want to approximate using Monte Carlo methods.
Yes. In some sense, we can call it a weighted Monte Carlo, which is weighted with this exponent minus e divided by kt. Just weighted Monte Carlo.
Yeah, I totally agree. But people say it's the original Markov Chain Monte Carlo, right? Because each update only takes the current state and changes it. So there's no like history to the system.
Yeah. I don't agree that it's weighted at all, Mike.
It's not weighted?
I don't think so.
You weight your samples. You weight your samples.
You don't weigh the samples. You don't.
No,
you
only if if it's a positive energy, then
no,
you add.
Even then, you don't weight it. You allow it with the probability. It's not weighting. It's
But
not weighting. It's either you accept it, or you don't accept it with this probability. You don't weigh the sample.
But
it can be you can discard the sample or accept it with this probability.
Exactly. Near, you're amazing. You're right.
And he's actually stating it. If C3 is greater than exponential of minus delta E over KT, we return it to its old position. Otherwise, we move it. They don't weight it. They accept it as is or don't accept it as is.
But isn't it equivalently to some weighting of these samples? Is it something different? I understand that it's a different algorithm. We don't weight with the samples, but our main objective is to sample our variable with the weight of exponent minus this minus energy. So okay, I need to think about it.
I think that the weight here is the number of particles that are accepted. So the number of particles that are accepted are proportional to exponent times the whole particles. The whole particles.
Yeah.
But the weight in terms of energy is not weighted. The energy is not weighted.
But you will converge your Markov chain with your building. It will converge. I don't remember in which sense it will converge, because there are several senses Markov chain can converge, but it will converge to the distribution which is imposed by exponent minus e in the minus e divided by kt. So it will converge to the steady state distribution, which is defined by this.
Yes, I agree. Yeah. That I agree with 100%, because that's the important sampling here. Yeah.
Okay.
And they say it is clear that with a large enough number of moves, will enable it to reach any point in the complete square. Since this is true for all particles, we may reach any point in the configuration space. Hence, the method is ergodic.
Okay.
And we talked about ergodicity in the past. And again, the assumption is here, instead of like looking at all the particles and how they're distributed, you can take one particle and like randomly generate new samples or new places it can visit. If it's ergodic, then those two views are equivalent.
By the way, do you remember, guys, the ergodic process converges to its steady state, or we should require some non-periodicity, because we have non-periodicity here, I guess, but I don't remember the definition of the ergodic process. Has ergodic process have to converge to its steady state, or not necessarily? I don't know.
I think what they mean is that if we take the mean over a lot of Monte Carlo states,
Yes.
It's kind of like
It's
it's the same as taking the mean over the whole sample space if we have it.
Yeah.
That's what they mean here. It's
yeah,
taking
it's
time domain
similar.
mean over the ensemble mean.
Yeah, it's like taking n particles, throw them in, and see what's happening. That will
Exactly.
give you a state.
Exactly.
Or if it's ergodic, it's mean like taking one by one,
Exactly.
throwing them, and getting a similar state. If this is equivalent, then it's ergodic, and they say it is ergodic.
Okay.
Mhm.
Okay.
I guess if it's not ergodic, then this mean is either this integral will not converge, or will not produce the same results.
Exactly.
What
It
we
won't
want.
be the same
Yeah.
result.
Yeah.
I think if it is not ergodic, the point you samples, it's this the distribution may not converge to the distribution which is imposed by exponent in minus
Mhm.
e
Yes.
divided by kt. Yes.
Agreed.
Okay, so we have another 5 minutes. So we won't continue. They give here some examples of
Mhm.
like a sphere and nice drawings of stuff, of lattice and spheres. But we won't go over it. I would like to ask you if you have used the MCMC in your work. In some cases, I'm curious.
I
I
don't think
haven't.
that you use it.
I
You have? Okay. So your
I
story is
I, I use the rejection sampling method,
Mm-hmm.
an importance
Interesting.
sampling, but not specifically in a Monte Carlo or sorry in a Markov chain.
Markov chain.
Yeah.
I think
yes. Okay.
I wanted to say if you use some Bayesian framework like PyMC, I think there are behind the scenes some Monte Carlo, Markov Chain Monte Carlo calculations happening, specifically to calculate posterior probabilities. I think,
Mhm.
again, that's happening behind the scene, but as a user of the library in Python, you don't really care. So I
Well,
think I've used that in the past,
you know
but
what?
not
I
explicitly, as I
take it
say.
back as well. I take it back as well now. Now that um, you sparked a thought that maybe my usage in the Kalman filtering and specifically in particle filtering is a form of the Monte Carlo Markov chain or Markov chain Monte Carlo method.
Yeah,
By the way,
so
yeah. By the way, I think MCMC Monte Carlo Markov chain is used also in machine learning, in deep learning. The purpose
mhm.
is a bit different. In machine learning, we usually don't want to compute some function, but we want only to sample, because what we have from this MCSC, we have a sample. We don't necessarily need to compute some function over the sample. Sometimes we need just sample. You have a very large data sets of images, and you want just to sample from the distribution which is imposed by this data set. And I remember that there are some papers that it is done with MCMC. I don't remember what was the additional mathematical framework they did it, but I'm pretty sure that I even reviewed a couple of such papers which used the MCMC for some in diffusion models paper, in the diffusion generative models. I'm pretty sure that there are a couple of papers which use the MCMC to improve sampling from this diffusion model.
Mhm.
So all of this stuff, Langevin dynamics and the Discord denoising and Monte Carlo and the rejection sampling and the Metropolis Hastings method, all this stuff is very, very connected.
Mhm.
Perfect. So we on good trajectory. Not sure what will be the next paper, but we'll find something interesting. And in the future, for sure, we should go into some search Monte Carlo methods. I think they are used today in LLMs for like chain of thought or some similar ideas.
Monte Carlo? How is Monte Carlo using the chain of thought?
Because think about it, you want to, if there's a question and now you want to generate different answers, so eventually you're gonna do a
Decoding.
search.
Yeah. It's not
Interesting.
I'm not sure it is search. It's some kind of decoding. You need to choose how you decode how you sample from the output the probability distribution of the tokens, conditional distribution of each generated token, and there are some methods, and the simplest parameter to do it is the temperature T. But there are many methods. By the way, I'm preparing some slide sets about fast decoding of LLMs, which hopefully will be ready in
Mike, what does it mean, decoding of LLMs?
Fast generating the LLMs. There are some methods, speculative decoding, and there are some methods which leverage Gauss-Seidel numerical method of iterative method of solving systems of equations. There are some very interesting methods which I came across, and hopefully I'll put it in some slide sets, and it's gonna be my next slide set, because
you're gonna publish it, Mike?
I'm going to give lectures about it. As once or twice in a year, I prepare some slide set, and I'm going to lecture in meetups and different conventions. It is not something proprietary. I'm going to talk about it a lot.
The problem with your lectures, Mike, you never record it. Not you. The lecture venue, they don't record it.
They record it. By the way, I gave lecture a month ago. I gave lecture about state space models in AI Dev conference, and it was recorded. And not only it was recorded, it was uploaded to YouTube. And the week before it, I gave a lecture on PyData, also about space state models, and it also was recorded and also uploaded to PyData. So most of the stuff I do is recorded.
Okay, good. I'll search for it.
Perfect. So now the listeners can search for it as well. And I guess we're gonna see everyone next week. I wish you a great week, everyone.
Bye.
Hey guys, have a great week.
Bye.